A very good morning to my dear students. Hope you all are well. I, Harita Malani, working as an assistant professor in Electronics and Communication Department of MLV Textile and Engineering College, Bhilwara. Today I am delivering my online lecture on subject fiber optic communication, which is in third year 6th sem of Electronics branch. Today I am delivering my online lecture on topic electro-optics, which is till now we have discussed various couplers, its applications, multiplexers, demultiplexers. Now we are today going to be discuss electro-optic switch. Whenever we consider electro-optic, it means that we need a conversion from electrical signal to optical to transmit optical light in communication system. So electro-optic switch is basically an active component. Till now we have discussed all the passive components. So it is an active switch. So we'll start with electro-optic switch. Traditional switch that connect optical fiber lines are electro-optic. They convert photons from input side to electrons internally in order to do the switching. So what they are doing, they are converting photons from the input side to electrons internally in order to do the switching and then convert back to photon on the output side. Here we use different micrometer ranges. So 1.3 micrometer electro-optic switch, silicon based optical switches have been fabricated which rely on refractive index change induced by injecting minority carriers. Multimode raised 2x2 structures are fabricated using epitaxial silicon and diffused homojunction. The first evidence of 1.3 micrometer optical switching is observed. So now we will study various types of electro-optic switch. So first I will discuss the passive bi-junction beam splitter. It is a type of coupler, but to design electro-optic active switch, I will require this passive bijunction beam splitter. So first I will discuss that, then we will continue with electro-optic switch. So first is passive bijunction beam splitter. So this is used where equal power division of the incident beam is required. Where it is used, this passive bijunction beam splitter is used where equal power distribution of incident beam is required. See, this is a structure having Y alphabet. We all know light input, the fiber core with refractive index N1, N2 are the cladding refractive index. So light beam will incident. It will be equally divided or equal power division of the incident beam will takes place and we will get two outputs. Okay, so this is passive bijunction beam splitter. A passive bijunction beam splitter fabricated from is shown in figure. So next I will study the passive bijunction beam splitter finds application where equal power division of the incident beam is required. Clear? However, the bijunction is of wider interest when it is fabricated from an electro-optic material, in which case it may be used as a switch. So when we are converting this as a switch, Y-junction beam splitter, when it is fabricated by using electro-optic material, then we can use it as a switch. Such material exhibit a change in refractive index del N, which is directly proportional to an applied electric field E following the equation. So this is the basic equation of refractive index. Change it. Del N is equal to plus minus half N1 cube small r E. What is N1? N1 is the original refractive index and R is the electro-optic coefficient. So next we will discuss active bijunction electro-optic switch. So active bijunction can be fabricated from a single crystal electro-optic material. So what we are doing here, we are using electrodes to which we will provide a biasing and which is managed near the optical fiber. So that is my active bijunction electro-optic switch. So metal electrodes are attached so that when biasing is applied, one side of the waveguide structure exhibits an increased refractive index while the value of refractive index on the other side is reduced. The light beam is therefore deflected towards the region of higher refractive index. See, we are applying biasing due to which the refractive index profile changes. So what happens? The light beam is therefore deflected towards the region of higher refractive index, causing it to follow the corresponding output ampers. So depending on the higher refractive index region, the beam will follow that path. Clear? Next, furthermore, the field is maintained in the electrodes which extend beyond the junction, ensuring continuation of the process. So this is the diagram of an electro-optic Y junction. Is it clear? So this is my light input, this is my optical fiber, these are my metal electrodes which are placed. Okay, biasing is provided, and this is my Y junction channel waveguide diffused in lithium niobate, and this is my output. So electrodes are placed. So it is an electro-optic active switch. So the light beam will be reflected more where the electrodes are placed and where the biasing is high. The refractive index will change accordingly. The output will change. The output waveform will change. Next, we will discuss regarding this only. With switching voltage around 30 volt, these devices prove to be quite efficient, allowing for larger junction angles to be tolerated than those of the passive bijunction optic material beam splitter as illustrated in the figure. However, a physical length of several hundred wavelengths is still required for the switch. So how much wavelength is required? Several hundred wavelengths is required. These devices therefore serve the function of optical signal routing. In addition, high-speed switches can be used to provide time division multiplexing of several lower bit channels onto a single mode fiber link. I can use the switch for TDM also. Okay, but for that I will use single mode fiber link. So is it clear? Next, I will discuss electro-optically switched directional coupler. We have studied in detail the directional coupler topic. We all know it very well. What do we mean by directional coupler? Its construction, its diagram. We know everything. So here we will discuss the switches may also be fabricated by placing two parallel strip waveguides in close proximity to each other as shown in figure. I will show you that figure also. We report the fabrication and testing of gallium arsenide electro-optic directional coupler switch in which the fraction of light coupled from one waveguide channel to the other can be controlled by an applied electric field. The evanescent fields generated outside the guiding region allow transverse coupling between the guides. Now we will discuss when there are two amplitudes, when the two waveguide modes have equal propagation constant beta with amplitude A and B as shown in figure, then the coupled mode equation may be written as. So this is the diagram of electro-optically switched directional coupler. Input light beam, it is coupled to this input light beam is traveling through this. These are my electrodes. This is my coupling region length. This is again one of my fiber input. Output coming from these are two waveguides X and Y. Electrodes are placed positive and negative. So waveguide will travel along. It will be coupled. You can get output at Y or at X. So electro-optically switched directional coupler. So the equations are dA by dz. Two waveguides we are considering A and B with amplitude A and B and having propagation constant beta. So the coupled mode equations are written as dA by dz j beta A plus jCB. dB by dz is equal to j beta B plus jCA, where C is the coupling coefficient per unit length. Assuming no losses, all the energy from waveguide X will be transferred to waveguide Y over a coupling length L0. Next, we will discuss the stepped delta B reversal coupler switch. It is very easy. Here we are using two more electrodes in the diagram to both the sides. In electrode structure which avoids the problem faced by the previous electro-optic switch, by dividing, so what we are doing here, we are dividing the electrodes into two halves with opposite polarities on each half as shown in figure. With this device, which is called the stepped delta B reversal coupler, it is always possible to obtain both the matched and mismatched cases described previously by applying suitable values of the reverse voltage. So this is my diagram of stepped delta B reversal coupler switch. Couplers are divided, these electrodes are divided in two halves, positive and negative. Two waveguides are there. So the signal will flow very easily and you can get output through this switch. So today I will wind up my topic here only. If you are having any doubt, any queries, you can ask, and students please study this topic, write down some important points, draw the diagram.